So there's a couple more important distributions. That's the main topic for today. Then we'll start Markov chains next time. All the remaining distributions are what I would call offshoots of the normal. That is, that their importance is inherited from the fact that the normal is important. They're all defined in terms of normal distributions, and their stories are tied to the stories of the normal, because they're just basically, we do different things with normal random variables. And the normal is so important. You know, we saw the central limit theorem last time, which is one reason that the normal is important, but there are a lot of other reasons the normal is important. And so you do things with the normal, then there's a good chance that that's also important, okay? So the first one is called the chi-squared distribution. It has one parameter. So it's chi, the Greek letter chi looks like a fancy x squared. Chi-squared of n. There's one parameter, n, which is called the degrees of freedom. Or in words, it's just chi-square. It's an extremely famous distribution in statistics. Some of you have probably heard of chi-squared test, or maybe even used chi-squared test, things like that. So we're not going to derive chi-squared tests in this class, but you would see that in a lot of other stat courses and other non-stat courses too. The chi-square test has become one of the most famous, statistical methods in psychology and sociology and all over the place. It's just used everywhere. And so to understand, you can get a computer to do a chi-square test for you, but to understand, and in some sense they're really overused for reasons that are not important to get into in this class, but to really understand what it's doing, you have to understand the chi-square distribution. So we're talking about as a distribution in probability, but it's used all over the place in statistics. So the definition, rather than defining it by writing down the PDF, which would tell you nothing about where it comes from, I want to define it in terms of how it's related to the normal distribution. Okay, so we say that, let's say, v equal, let's say, z1 squared plus z2 squared plus blah, 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 plus zn squared, where the zj's are IID standard normal. That's the definition of how we get a chi-squared distribution. So then, by definition, just to write that down, by definition, this is chi-squared, and we would just write v is chi-squared of n. So sometimes the n gets subscripted, sometimes it's written like that, so same thing. So all it is the sum of squares of n IID standard normals. Okay? And this comes up a lot in statistics because a lot of statistical methods somehow involve adding up squares of things, right? And if those things happen to be IID standard normal, then you're going to get chi-squared. So it comes up everywhere. All right. Well, that's all as far as the definition, but I want to show you how does it connect with other distributions we've done. So I'll just call this fact. Chi-squared of 1. Chi-squared of 1 means we just take one standard normal and square it. Chi-squared of 1 is the same thing as gamma of 1/2, 1/2. That's not something that you can easily see in your head, but it's a calculation that you could all do it at this point. It's good practice, so I'll let you do this. The reason, just do the change of variables thing. The reason I'm not going to go through the algebra of this is because you had a homework problem where we took a standard normal and raised it to the 4th power, and you found the PDF, right? So this is like an easier version of that problem. It's the same idea. The only thing you have to be careful about is because it's squared, then you have to deal with the fact that the function, y equals x squared, is decreasing and then increasing, right? So you can't just plug into the change of variables formula. As long as you're careful about that fact, though, it's just an easier version of that homework problem. You can just do the calculation, get the PDF, same as on the homework. So if you understood that homework problem, then this is easy to check. And you just get the PDF, and you'll see, oh, that's the same as the gamma 1/2, 1/2. So that's a useful fact about the chi-squared, because we already know a lot of nice things about the gamma. We know how it relates to the beta. We know how to add up gammas, and we know how to get moments for the gamma, things like that. we can borrow all the stuff we know about the gamma distribution and just use that for free without having to rederive everything. So that's very helpful in studying chi-squared. That's chi-squared of 1. So assuming this fact, which you can just check, like on the homework problem, now if we want chi-squared of n, that just says we're adding up n IID gamma 1/2 1/2, right? And remember, we also talked about the fact that if you have a gamma A lambda and gamma B lambda and they're independent and you add them, you get gamma A plus B lambda, right? So therefore, if you add up n of them and the lambda is 1/2, that's the same for all of them, same scale, just adding up with a 1/2. So it immediately follows from this that chi-squared of n is the same thing as gamma n over 2 1/2. So this is really actually not a new distribution. It's a new name for something we already knew, which is a gamma. Okay, so in a sense, I don't really need to list it separately on the table of famous distributions or things like that. It's a special case of the gamma. But it's used so much in statistics because of adding up sums of squares that it gets its own name and it gets its own entry in the table. Okay, so that is the chi-squared distribution. That's our penultimate famous univariate distribution. That univariate as in it's not multivariate. We're going to also do the multivariate normal today. Just foreshadowing that, we talked about the multinomial distribution, right, which is the generalization of the binomial when you have more than 2 categories. So the multinomial is the most important multivariate discrete distribution, right? It's discrete. It's a generalization of the binomial. The multivariate normal, which we're going to do later today, is the most important multivariate continuous distribution. So it's just what the question is, what's the natural way to extend normal distribution into higher dimensions where you have a vector rather than just one random variable. You have a random vector, okay? And so we'll talk about that later. But first we just need one more univariate distribution, which is the famous student t distribution. A lot of students have wondered why it's called student, and the reason is that it was discovered and first used by a guy called Gosset. Well, the fact that his name is Gosset doesn't tell you much about why is it called student then. The reason, this was around 1908 that he first introduced this in a very influential paper. Gosset was a statistician who was working as a master brewer for Guinness, that beer company, and he was an excellent statistician working for Guinness a little over 100 years ago, and a lot of people think that, and so when he was publishing his papers, he used the pseudonym student, and a lot of people think that was because he didn't want Guinness to know, but actually Guinness was very supportive of him as far as I know, but Guinness did not want the other beer companies to know that they had a statistician working for them, because that was like their secret weapon. So he published his papers using the name student. It was just a pseudonym he came up with. The letter T was just because it became standard to use the letter T for a certain statistic. So those of you who have seen T statistics or t-tests before, it just got called T for some reason, and that caught on. Okay, what he introduced with the t-test, which is based on the t distribution, which we're about to do, 100 years ago, just over 100 years ago, but then since it caught on, it's been extremely widely used in statistics, and it still is to this day. So I just want to say a little. We're not going to go through like a lot of the statistical side of how do you use t-tests and one sample t-test and two sample t-tests, things like that. Some of you have seen, but I'm not assuming that you have. But the reason, the mathematical basis behind those things is the t distribution. So we're going to talk about the t distribution. Okay, so again, we could write down the PDF of this thing. but it's just this complicated looking thing, and it will give you no idea of where does it come from. So again, we're going to define it by relating it back to the normal distribution. Okay, so we're going to say that let's let T, call it T because it's going to be a T distribution. So suppose we have a random variable T that's of the form Z over the square root of V over N, where Z is again standard normal, and V is chi-squared of N, and they're independent. So Z is independent of V. Okay? So if we have a random variable of this form, we say that follows a T distribution. And we would write that as T is distributed as T sub N. Lowercase t is the name of the distribution. We don't necessarily always write the student. We just say, T distribution, N degrees of freedom. Degrees of freedom is just a mysterious at first sounding name for what the parameter is. And it's kind of a deep question, like what do degrees of freedom really mean, and how people talk about degrees of freedom. But for now, you can just think of that as the parameter, which goes back to the chi-squared. It's just how many normals squared did we add up? We call that the degrees of freedom. That's the parameter. On top, it's just one standard normal. But here we have a chi-squared of N, so that's where the parameter comes in. All right, so that's the T distribution. Let's just mention a few properties that we can see. We could get the PDF of this thing by doing an ugly Jacobian type of calculation, but there's no need for that for our purposes here. I mean, I'm not saying you'd never need the PDF of this thing, but for the things that make it interesting for our purposes, we can just think of it in terms of this representation in terms of normals. Okay, so first of all, let's just stare at this and see, what can we say about it. First of all, it's a symmetric distribution. That is, if we multiply by -1, it has the same distribution. So it's symmetric about 0. And you can see that just by multiplying by -1. And we know that the z is symmetric, right? The normal 0, 1 is symmetric about 0. They put a minus up here. That doesn't change the distribution on top, and the bottom is just some independent thing that hasn't changed. So it's symmetric. Let's look at the case n equals 1. If n equals 1, then we just have the square root of a squared normal, so that's the absolute value of a normal. So what we have in that case is a ratio of independent standard normals with an absolute value sign on the bottom. But the absolute value sign on the bottom does not affect the distribution, again, because of symmetry. So if n equals 1, it's really just the ratio of two independent standard normals. And that's the distribution we saw before, the Cauchy. So this is a generalization of the Cauchy. So T1 is the same as Cauchy. Remember, we did that Cauchy interview problem. We derived the PDF of the Cauchy and things like that. So this generalizes that. And in particular, the mean doesn't exist. We were talking about the evil Cauchy before. Cauchy does not have a finite expectation. So the T distribution with 1 degree of freedom does not have a finite mean. The mean doesn't exist. But on the other hand, if n is at least 2, then by symmetry, the expected value equals 0. Symmetry is one way to see it, but let's also do just a quick calculation for why the mean is 0. So you had another homework problem pointing out that in general you can't say E of this ratio. In general, that's not going to be E of this over E of that, right? But it is true that we can write this as E of z times E of 1 over square root of v over n. That's valid because this piece and this piece are independent. I assumed that they were independent, right? They're independent, therefore they're uncorrelated, so we can do that. And we get 0. The reason this would break down in the case of n equals 1 is that this term wouldn't exist. And you can't say that something that doesn't exist times 0, you can't say that that's 0, right? So that's the problem, okay? But as long as this part exists, which it will if n is at least 2, then it's 0. You can also just see, that had to be true, but by symmetry, that the mean is 0, okay? And so it doesn't have an MGF. It doesn't have all of its moments. Like the T1 doesn't have a first moment. The T2 won't have a second moment. The T3 won't have a third moment. It goes like that. So there's a limited number of moments you can take. And actually, if you want to get, so I did this for a first moment. But if you want to get a higher moment, if it exists, all you have to do is put this T to a power, right? And then just put the power here. We get all that from things we know then, right? Because we know all the moments of the normal. And then this one here, you raise that to a power. It looks ugly the way I wrote it. But if you just imagine raising this thing to a power, that's just a power, there's some constant that you can take out. Aside from that, it's just a power of a gamma distribution, right? And powers of gamma distributions, it's easy to get the mean using Lotus. So that means we can find the moments that exist. It's not true that all of its moments exist, but the ones that do, we can find in an easy way using this. Now, the odd moments are going to be 0 if they exist by symmetry. If you put like z cubed here, then that's going to be 0. But for the even ones, we talked before about the even moments of the normal, and then this. Oh, actually, here's another way to get this is just a reminder of the moments, even moments of the normal. E of z squared is 1 because that's the variance. If z is standard normal, e of z to the 4th is 3. E of z to the 6th is 3 times 5, and then it goes up like that, where you're multiplying. This is 1 times 3, 1 times 3 times 5, blah, blah, blah. It's a skip factorial. We proved that before using MGFs, right? But here's another way to look at this problem. If we wanted, so we used MGFs before. Another way would be to relate it to gamma by relating it to chi squared. So if we have the expected value of z to the 2n, that is, we want the 2nth moment of a standard normal, where n is a positive integer. Well, we could just think of that as e of z squared to the n. That doesn't take much algebra. But the point of writing it this way is now we recognize, oh, z squared, that's just chi squared of 1, right? But chi squared of 1 is the same thing as gamma of 1/2, 1/2. So all we really need is the nth moment of a gamma 1/2, 1/2. Then you can just use Lotus. So we did a calculation before using Lotus to get the moments of the gamma, and for practice, if you don't, it doesn't matter if you remember that or memorize that, but you should be able to do the Lotus. In the gamma function, it's really easy to get moments, right? The gamma distribution, it's easy to get the moments because you just go, x to a power times this gamma thing, but then it still looks like a gamma, right? So as soon as as long as you have the pattern recognition of the gamma integral and you write down Lotus, you can get this. Okay, so if you do it this way, you're going to get something in terms of the gamma function, but you can show using properties of the gamma function that is in fact equivalent to just these multiplying odd numbers. Okay, so all right, so that's how we can get the moments of the t distribution up to the point where they stop existing. Okay, and other properties. Well, one reason that the t is famous is that it looks like the normal distribution approximately, but it's heavier tailed. And the easiest way to see that is just to see it by trying it out, plot what the density looks like or generate some values. So heavier tails meaning that, more extreme values are relatively more likely than they would be for the normal, and heavier tailed than the normal. You can measure that in terms of kurtosis, for example, which is on the homework you just turned in, or just by looking at it. And that's especially true if n is small, like in the Cauchy has very, very heavy tails. The Cauchy density was a constant times 1 over 1 plus x squared. So as you let x go to infinity, the Cauchy is decaying like 1 over x squared, right? Try comparing that with the normal. The normal, you have e to the minus x squared over 2. But the normal is decaying much, 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 much faster than a Cauchy. But on the other hand, to relate it more to the normal, if n is large, like let's say n is 30 or 40 or 50 or larger, then it really just looks like a normal. So for n large, Tn looks very much like standard normal. And when I say looks very much like, I'm using that kind of intuitively, but if you want a mathematical statement of it, let's just take the limit. So a math statement would be that the distribution, either the CDF or the PDF, either way, will converge to the distribution of standard normal if you let n go to infinity. And to see that, well, you could do a big calculation, but it's not necessary. That the best way to see that is to use the law of large numbers. So let's actually check that fact over here. Okay, so now let's imagine, to make it clear, I didn't indicate the dependence on n here, but to make that clearer, because we're taking a limit, let's consider a sequence of them. So let's let Tn equal z over square root of Vn over n, where let's say we have an infinite sequence of IID standard normals. Okay, so we have all these IID standard normals, and what do we do with them? Well, that's supposed to be a chi-squared of n, so Vn is the sum of squares of normals. Okay, so I'm just generating a t distribution with n degrees of freedom. May as well just use the same z for all of them, right? Those are independent and so z is also standard normal, and it's independent of the zj's. So this is a way to construct a t distribution with n degrees of freedom, just by the definition over there. I took a normal divided by then this chi-squared thing, okay? But I chose to define it because I'm just looking at what happens with the distribution. I'm saying what happens to the distribution of this as n goes to infinity. We can choose whatever t random variable we want as long as it has the correct distribution, right? So, okay, so let's choose it this way, using the same z each time. That makes it easier, right? Same z. Then what happens? Let's look at this thing Vn over n. What do you think happens to that as you let n go to infinity? It goes to a constant. Which constant? Converges. Well, if I took a sample mean of these, and I look at the, yeah. So I mean, you can think of this as the sample mean of these squared normals. So its distribution. If we standardize this, then in distribution it'll go to normal 0, 1 after we standardize it, but I just want something simpler than that. What does it converge to point-wise? It converges to 1. Why'd you say 1? From this? Using what theorem? Law of large numbers. CLT will let us get the distribution of this, but I just want to say what happens to this point-wise. That is, if you evaluate this at each point in the sample space. So this goes to 1 with probability 1 by the law of large numbers, because we're taking these n IID squared normals and we averaged them, right? And the law of large numbers says that the average of the sample converges to the true theoretical average. The true theoretical average is just the expected value of one of these, right? Their IID. Law of large numbers says this will converge to the theoretical value, E of z1 squared, which is just 1. That's the variance of z1. So this thing goes to 1 with probability 1. There's a square root there, but because this is just a point-wise statement, this converges to 1. If we take square roots, it still converges to 1. Square root of 1 is 1 with probability 1. Okay? So now we're letting n go to infinity, but the denominator is just going to 1. So this sequence, Tn, is just converging to z with probability 1. That's telling us that these random variables converge because I constructed it this way. I could have constructed the t distribution some other way. I didn't have to use the same z and the same z1 squares and keep recycling things this way. We could have chosen some other t distributions, but the distribution, so this point-wise statement might not be true anymore, but the distributions are still behaving this way. So what that says is that the t distribution with n degrees of freedom converges, now I'm talking about the distribution, not the random variable, converges to a standard normal distribution. So if n is very large, then you're just thinking of this denominator as being essentially 1 by the law of large numbers, and so then what matters is the normal on top. Okay? So if you have a large number of degrees of freedom, it just looks like the normal distribution. Okay? But with a small number of degrees of freedom, then it looks sort of like the normal, but it will have much heavier tails. Okay? All right, so that's really all you need to know is for univariate, famous, named distributions. Okay? So last topic for today, and our last famous distribution, is the multivariate normal. And so what we want to do is extend some of the nice stuff for the univariate normal, right? Normal has a lot of nice properties, very, very useful. But what if we have a random vector, not a random variable? Okay, so there's one case where it would be really easy to construct a multivariate distribution, which is if we have independent random variables, right? If we have independent, let's say we have IID random variables, just stick them together into a vector, and they have a joint distribution. But that's a simple case where the joint, if it's continuous, the joint PDF is the product of the marginal PDFs, and that the more interesting cases, as far as like a multivariate perspective, is when there's some correlation. Okay, and it turns out that for the multivariate, for the normal, there's a very, very nice standard way to extend it to higher dimensions. And there's different equivalent ways to define this. So we want the multivariate normal, which I sometimes abbreviate to MVN. Well, we have to start by defining it. And there's different ways to define it, but I think the nicest way for our purposes is to define it in terms of linear combinations. That is, every distribution we're talking about today, the way we're thinking of it is by reducing it back to stuff we already know about the normal distribution, right? Chi-squared we defined in terms of the normal. T was defined in terms of normal and chi-squared, but in turn that's defined in terms of normal. And we're going to define multivariate normal in terms of just normal, right? Everything is based on the normal distribution today. Okay, so if we have a vector, a random vector just means that we have a bunch of random variables that we strung together into a vector. So let's say we have a random vector, let's say x1, x2, xk, which maybe we'll just call that vector x, okay? And the definition is that this is multivariate normal if the following is true. If I want to reduce this back down to the one dimension, right? Reduce it back down to the case we're familiar with, which is the one-dimensional case. A natural way to do that is just to take a combination of the components. So if every linear combination if you haven't had linear algebra, linear combination just means add up these variables with any constants in front. So a linear combination just looks like, let's say, t1, x1 plus t2, x2. That's just called a linear combination, if you haven't seen that before. So I took a combination of the random variables. T1 through tk are just arbitrary constants, any constants at all. Okay, if this is always normal, every linear combination. So if you can choose even one choice for the t's for which this fails to be normal, then it would not be multivariate normal. But if no matter how you choose these constants t, this always has a normal distribution, then we say it's multivariate normal. Okay? So see how this reduced it back down to one dimension? Now this is just a random variable. Okay, so we've reduced it back down to familiar things. So for a couple quick examples, let's do a quick example that is multivariate normal and a quick example that is not multivariate normal. So suppose that we started with, let's say, z and w be IID standard normal. Then, well, of course it's going to be true that z comma w is multivariate normal because they're just independent, but it's more interesting if there's some correlation between them. So for example, what if we did, you know, z plus 2w, I'm just making up some numbers here. You can put whatever constants you want. I'm just doing a concrete example. 3z, let's say we did 3z plus 5w. I just made up some constants here. Is multivariate normal. So this is a vector now. I took these IID standard normals and then I just added them with some constants I just made up. You know, of course I could put A, B, C, D here. That will be true. Just wanted to have something a little more concrete. Okay, so why is that true? Well, to verify that this is true, all we need to do is to say if we take any constant times this plus any constant times this, it is normal. So if I take, let's call the constants s and t, s times z plus t 2w plus t times 3z plus 5w. I just took two arbitrary constants in front, s and t are any constants, and rewrite this in terms of z and w. That is something times z plus something times w. Well, that's just s plus 3t z plus 2s plus 5tw, and that's normal. Because we already knew that if we add up, right, if we already knew from using MGFs and previous stuff we did, we already knew that if we add up independent normals, it's normal, right? So this is one independent normal plus, this is the sum of two independent normals, so we know that that's normal. So that's just an example, but that's kind of an important general class of examples that we start with IID normals and then just, put together a vector of different linear combinations. That will always be multivariate normal. All right, so that's an example. Let's do a non-example. I don't know if non-example is the right word. I want to go as far away from that example as possible. I'm not going to say counterexample, because it's not a counterexample to anything. It's just an example that's not a multivariate norm. Well, sort of a counterexample, but I'll call it a non-example. Non-example would be let z be standard normal, and let's let S be a random sign. That is, S is plus or minus 1 with equal probabilities, and it's independent of Z. Okay, so then Z and SZ, S times Z is related very closely to one of the strategic practice problems from before, or you can check for yourself. Multiplied by a random sign, just through the symmetry of the normal, that's still standard normal. So marginally, these are our standard normal. Marginally meaning if you look at Z on its own, look at S times Z on its own, they're just standard normal. But the pair Z, SZ is not multivariate normal. So put them together, on their own, they're normal. Put them together, it's not. The reason is that we could just look at Z plus SZ. If you want to test whether this is multivariate normal, according to the definition, you need to check what if I take something times this plus something times this. Well, the easiest case of that would be to simply add them. Z plus SZ, there's no possible way that that could be normal, because if you look at what happens, half the time S is minus 1 and you get 0. The other half the time you get some continuous thing. So this is actually a mixture of discrete and continuous. You're never going to find a normal distribution that equals 0 with probability equal to 1/2, right? That is not a property of the normal distribution. So that's not multivariate normal. And you can see that this definition, if in our definition, if we had decided to just like say, well, multivariate normal just means you just string together some normals, then we'd be including this example. But this is a pretty nasty example, right? So we're avoiding things like that by defining it this way. So that's much better. Okay, so, well, we haven't done the PDF or the MGF. The MGF of the multivariate normal, we don't really need for this course. I mean, you can do some Jacobians and work it out. MGFs are much more useful for our purpose, much simpler. So let's derive the MGF. This is a joint, the MGF. So this is the MGF of a joint distribution of X. So let X be multivariate normal. Okay. Now, so since this is multivariate, when you define the MGF, you do it like with a constant times each term. That is, you know, in the univariate case we just do e to the tx. In the multivariate case we have a linear combination e to the t. I'm going to write it this way, t prime x, where this just means take the vector of t and do a dot product with the vector of x. In other words, to write that out more longhand, this is just the definition of the MGF, is that we need a constant for each component. So it's e to the t1 x1 plus blah, 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 plus tk xk. Right? Okay. So that looks like it might be a complicated thing. We're assuming we have a multivariate normal. We want to see what does the MGF look like. Well, it would be this, but what can we say about this? Well, it looks like this may be very complicated until we think back again to the definition we just did. The definition said that if we are requiring this to be multivariate normal, then the thing up in the exponent is normal, right? So all we really have is the expected value of e to a certain normal random variable. But that we can get from the MGF of the normal in the one-dimensional case, right? So we've reduced it back down to one dimension. And in particular, if you look up the MGF of the standard normal, I'll just write it here for reference sake. If let's say x is normal mu sigma squared, I'll just remind you of the MGF, which we've done before. The MGF of x, the way I remember it is that it's e to the power of the mean of what's up here, which is t mu. I just took the mean of this, plus 1/2 the variance. That's just what the MGF works out to. So the variance of this is t squared sigma squared. So that's the MGF of a standard normal would be the case mu equals 0, sigma equals 1. That's the MGF of any univariate normal. But if we know that fact, which we did earlier, then we just know right away what this is. By definition, that's just e to a normal. That's a special case of the MGF. Oh, in particular, if you just want, instead you have e to a normal, you could just let t equal 1 if you want, right? You can let t be anything. Okay, so to sum that up, we already know, without doing any more calculations, we already know that this is going to be e to the expected value of what's up here, which is, let's say, t1 mu1 plus blah, 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 plus tk mu k, where mu j is let's just let e of xj equal mu j. That's the mean. So mu j is the mean of the jth component just viewed on its own, all right? And then plus 1/2 the variance, so that's e to this whole big thing, 1/2 the variance of this thing. I'm just going to write it as variance of that thing. So that's all up in the exponent. I guess it's a little, let me just write it as exp. That means e to the power of this thing. Okay, just the mean of what's up here plus 1/2 the variance. And then to get this variance thing, if they're independent, then we can add up these variances. But it might be that there's some covariances between them, and then we would just expand this out in the way we usually get variances. So that's the MGF, and for multivariate distributions, it's true just like for univariate that if you know the MGF determines the distribution. Okay, well, so one more property of multivariate normal. Last fact about it is a very, very useful fact about independence and correlation. So that's the fact that within an MVN, that is, if you have this multivariate normal vector and you kind of look inside that vector, then it's true that uncorrelated implies independent. We saw before that in general, independent implies uncorrelated, but uncorrelated does not imply independent. But a very important special case where the converse is true is when you're working within a multivariate normal, implies independent. In other words, just to write this out, if we let x equal, so that's our vector, but let's say we split it up into like x1 and x2, MVN. So we have a multivariate normal and we split it up into two vectors. Then the statement is that if every component of x1 is independent of is uncorrelated with every component of x2, then they're independent. So take any component of x1 and look at the covariance between that and any component of x2. And if they're all 0, then x1 and x2 are independent. So x1 is independent of x2. So like that would not be, if we allowed weird examples like this one, then that statement would not be true because z and s times z are clearly not independent. But they are uncorrelated, because if you compute the covariance of this and this, you get 0. So you can't say, so these are normal and they're uncorrelated. That doesn't imply that they're independent. But with the multivariate normal, that is true. So for a quick example of this, suppose we had x plus y and x minus y. So let's let xy be IID standard normal. Okay, and consider the sum and the difference. Okay, so x plus y and x minus y taken together as a vector. That's multivariate normal. We'd probably call it bivariate normal in this case. When it's two-dimensional, it's also called bivariate normal. That's multivariate normal for the same reason we just saw. That is, if you take any constant times this plus constant times this, it's normal. So therefore, it's multivariate normal. And they're uncorrelated because if we take the covariance of x plus y and x minus y and just expand that out, it's the covariance of x with itself. That's the variance of x. And then it's plus covariance of x and y, but from this one, but there's also a minus covariance of x and y from those two, so those cancel. And then there's minus the covariance of y with itself, so that's minus the variance of y. So this cancels, and because they both have variance 1, or in general, if they both had the same variance here, the variances cancel, we get 0. So they're uncorrelated. The sum and difference of IID standard normal are uncorrelated. In general, uncorrelated would not tell us independent, but here, because they're multivariate normal, we now know that x plus y and x minus y are independent. That's another very special fact about the normal. It's very difficult to prove, but it turns out to be true that if we did here IID anything other than a normal distribution here, and if it were true that this is independent of that, then actually it would have to be a normal distribution. So this is a very special property of the normal distribution. And the proof is just, from this fact about multivariate normal. Okay, so to prove this fact, you can just do a calculation with MGFs that we don't have time for and that you don't need to worry about, although you could do it for practice with the MGF if you want. But anyway, knowing this result is very useful because it's often easier to compute the covariance than to directly show they're independent.